So we're just going to start where we left off last time. We had talked a lot about flux, electric flux through a surface, and we did the example of calculating the electric flux of through a sphere that is centered at which the center resides a point charge, and we found that it was constant; it didn't depend on distance. And I promised that would actually generalize. So let's talk about Gauss's law. I guess my wife likes to use blue. Let's talk about Gauss's law. Right. So what we should have realized from last time, hopefully, is, or maybe if you didn't realize it, then I can tell you, is that the shape and size of the surface when computing flux, or shape and size of the surface surrounding the point charge that we talked about last time, is irrelevant. So long as the surface is closed. So a closed surface just means that the surface is like there's a well-defined inside and a well-defined outside. Think of it like anything, or put another way, it doesn't have an edge. Like you can imagine that a square has an edge, right? But a sphere doesn't have an edge. Like a hollow sphere doesn't have an edge. It's like there's no place where it just abruptly stops if you're traveling along it, right? So that's what it means. That's what closed means. But the reason why the shape and the size of the surface doesn't matter when it's surrounding the point charge is because well, first of all, we showed that the size doesn't matter, right? The size didn't matter because if you make the sphere bigger, it's independent of the size. And the shape doesn't matter because regardless, you're still counting the same number of field lines leaving that shape or leaving that surface, exiting the surface. So regardless of like how wobbly the thing is, it still has the same number of flux lines. And even if it like backs in on itself, you'll have the same number of flux lines or of net flux lines exiting. You'll have maybe 2 more exiting, but you'll have 2, you'll also have 2 entering. And so those cancel out. It also follows from our discussion of superposition that the distribution of point charges, or of, they don't even have to be point charges, the distribution of the charge inside the surface is also irrelevant. The only thing that matters is the amount of charge inside the surface. So it should be kind of easy to see why that's the case. Imagine that you had a sphere centered around a single point charge. And let's say we had another point charge here. Well, we know that all of these integrals are additive, right? Well, actually, let me write some words as an explanation. So any point charge Q produces some amount of flux, and that amount is Q over epsilon naught, right? That was what we calculated last time through, and this is through any surface, which encloses it. Further, so dipoles would have 0 flux, precisely, as long as you completely surround the dipole. So further, flux is additive. And that's just, flux is additive because the electric field is additive. i.e., if you have the flux through one surface of one charge, and then you have the flux through the same surface, but for a different charge, maybe somewhere else or of a different value. If you want to find the flux for both charges combined through that surface, that would just be the sum of the fluxes for each individual charges, just because the electric fields add up. And all we're doing is we're integrating an electric field. And so you can split an integral however you want. So the end result is that the flux through any closed surface, any closed surface which encloses a total charge Q, I'm going to call it Q enclosed, is given by E dot dA. This is the formula for the flux, and this is an integral over the surface. By the way, this little loop, that just means that the surface is closed. Like a loop on the integral means that the surface is closed. It doesn't have boundaries. This is just equal to the enclosed charge divided by epsilon naught. And so this statement here, let me move it down a little bit. This equation, this is Gauss's law. Or at least it's the integral form. So let's just look at this for just a second. So why should this be true? Well, clearly this is true for if the surface is a sphere and the enclosed charge is a point charge, right? We already showed that that's the case because we just calculated the flux from a point charge because we know the electric field through a surface which happened to be a sphere of some radius, and that was equal to the charge of the charge of the point charge divided by epsilon naught. It says ENC, stands for enclosed. It is enclosed by the surface. So say you then have 2 point charges. You have a point charge here and a point charge here, right? So we could just put any shape around just one of them, and it would still have, say this is plus Q1, and then we have, we can put any shape around that charge, and by the argument that we made above, the flux through this would still be flux of, say, Q1 is still Q1 divided by epsilon naught. But now let's say that we have another charge, say plus Q2. This is also going to have some electric field, but the electric fields add up. And so the flux through the same surface for Q2 would just be Q2 over epsilon naught. And so because the flux is just an integral of the electric field, the total electric field, which is just the electric field from the individual parts, can be written as it's just a sum, right? That's superposition of electric fields. And so the integral of the electric field, this is the total flux for both charges, dot dA, this should be equal to an integral over the surface over the surface of E1 plus E2, or Q1 Q2 dot dA. And so we could split up the integral into the flux from charge 1 plus the flux up from charge 2, and we already know what those are. And so the fluxes add, so we're left with Q1 over epsilon naught plus Q2 over epsilon naught. That's just from these two results here. And that is just the total charge enclosed divided by epsilon naught, because Q1 plus Q2 is the total charge enclosed. And so then you can imagine doing this for any number of enclosed charges, or for indeed a continuous charge distribution, like a blob made out of charge that has some charge distribution on it, and it will still work because the electric field is additive. And so the point is even though we only derived it for a point charge, because of the technical term would be the topology of the surface, it doesn't matter what the charges look on the inside. All that matters is how much charge is enclosed, and that will tell you how to compute the flux, or that will just explicitly tell you the flux, and you can use the flux to learn about what the electric field is. So just as a quick convention, oh, and I want to point to this, that is the electric flux. So as a quick convention, the direction of the infinitesimal vector dA is set to be, by convention, it dA points out of the surface. So you can reasonably say that there's an inside and an outside of any closed surface. So dA points in the direction that that goes outward. And so the end result of this convention is that the flux is positive for positive charges, or for positive enclosed charge. Yeah, so it would be the outward normal, and it's negative for negative enclosed charge. So when we say that the flux is positive, we mean that there are more field lines going out of the surface than there are field lines coming into the surface. So I want to show you a quick example. Let me see if I can pull it up really quick. Sorry. It's in the, I have a link, but I don't remember what the link said. It's in the textbook, so I'll just write, this is an example. I want to just describe it to you so you don't have to go in blind. It's in section 1.6. And it is sorry, one more time? Yeah, I can scroll up. Oh, yeah, so the example that I wanted to just make you aware of is using Gauss's law, which is the equation that I put in a box. Using Gauss's law to solve for the flux through a disk above a charge. So I showed you the example. I didn't actually work it out, but I pointed you to the example where you solve that just by computing the flux by doing the integral. The example 1.6.2 will actually go through doing the same example using Gauss's law, and it's significantly easier. There's another example that you can see in the text. This is section 1.6, EX 1.6.2. There's another useful example that you guys might get a kick out of, which is the electric flux through a square above a point charge. And that is similarly, it is in section 1.6, and it is example 1.6.3. There's also a few other examples just of more Gauss's law type problems in the textbook, in like the university physics textbook, which I've linked to in the lecture notes. So go take a look at those if you want more examples and more practice. Right. So so Gauss's law is not just in this form. It's not just this. Notice that I wrote that it's the integral form. So in fact, there's another form of Gauss's law, which is called the local form. And we won't be using this a whole lot, but it is very useful to know, especially because there are some situations where you can only use the local form. So this is going to make you hate me, because you guys have to remember now some math from 21C or 21D. It requires the divergence theorem, which hopefully you remember. This is from calculus. Now, the notation that I'm going to use might be different from what you've seen, but the way that at least I was taught the divergence theorem when I was in high school or whatever, is that you have an integral over a closed surface, so it's a double integral, over the surface S of some vector field dotted into the normal dA equals an integral. Why do I have a D there? That shouldn't be there. An integral over the volume that is enclosed by that surface of the divergence of the vector field times the volume element. So this is the divergence theorem. You can go check your math textbook. It's usually written like precisely like this. They might use V instead of F, but whatever it is, hopefully you've seen this before. We can rewrite this using our language and our notation. This integral becomes, we just only use one integral symbol, but that's just a notation thing. And then we would integrate over a surface And then we would have f, instead of f dot n dA, this is just f dot dA. All we do is we combine the n hat and the dA into the vector dA, and this is equal to an integral over an enclosed volume by that surface of grad f dV. So this is just how I would write it in a more physicsy context. That's all. So we can apply this to Gauss's law. So remember that Gauss's law has, on the left-hand side, it has E dot dA. And so we can replace the left-hand side of Gauss's law with the divergence of E dV. So Gauss's law becomes an integral over the enclosed volume of the divergence of E dV, and that's equal to the enclosed charge divided by epsilon naught. What's after the first f? It's a dot n. It's an n hat. It's like the unit normal. There we go. But so this Q enclosed, now it's really the total charge in the enclosed volume. And so note that the total charge in the enclosed volume is just the integral over the volume of the charge density. It's just the integral of rho dV, where your domain of integration is the enclosed volume. And so what we're left with is we can plug this in, and we're left with two integrals over the same thing. I'm just going to put vol here of del dot E dV equals an integral over the volume of rho over epsilon naught dV. And so you're not usually supposed to do this. Can you explain how the f turns into an E and the integral? The f, this is just some arbitrary, it's just some arbitrary, it's not force, it's some arbitrary vector field f. It's just some, like, this is just true of any vector field f. This is just a true statement. So we apply it to the electric field, which is also a vector field. And so, yeah, I just wrote down the divergence theorem. Like that's all the divergence theorem is. And then we're just applying the divergence theorem to Gauss's law. Right. So then the next thing to note is that we're doing the same integral on both sides. And so while you're not really supposed to do this, we can kind of just cancel the integrals. And so you're left with del dot E equals rho over epsilon naught. Now, yeah, that's a rho. Now note that rho is not necessarily constant. But neither is the gradient of, or the divergence of E, right, of the electric field. Like, neither of them have to be constant. And so this is just a relationship between a function, which is the volumetric charge density, and the gradient of the divergence of a vector field, which is also just a function. And this is just saying those two functions are the same. So this statement here, this is the local form of Gauss's law. It is 100% equivalent to the integral form. It's just one is more useful than the other in some cases. Yeah, it's constant if the charge is uniformly distributed. That's true. Right. So this formula, this form of Gauss's law, again, it can be very useful for the same type of problem actually as the integral form is, but it's particularly useful when you know something specific about the positional dependence of the electric field. Like if you know that the electric field is, say, x squared in the I hat direction plus, I don't know, y squared in the z or in the j hat direction or whatever. If you just know what the electric field is, you can just take the divergence of it automatically and get the what charges have to be present for that electric field to be what it is, i.e. what charges produce that electric field. So just as a quick appendix, I'm not actually going to spend time going over this in lecture, but in the lecture notes and in the textbook, there's just a quick bit on what the divergence is of various coordinate systems. You guys probably are familiar with it like super easily in Cartesian, where it's just the sum of the partial derivatives. I also give it to you in cylindrical coordinates, that assuming the field only has radial dependence, and similarly for the spherical coordinates. So go take a look at those if you want a refresher on the divergence in different coordinate systems. Rho is the volumetric charge density. It's how much charge is in a given, it's the amount of charge per cubic meter in a given location. So just an example of using using the local form to find the electric field at a given point, you can see section 1.6, example 1.6.4. Right. So for the remainder, not for the remainder, well, maybe, depends on how long this takes. For the next significant chunk of lecture, we're just going to do practice, going over applications of Gauss's law. Because it's going to be probably your best friend when it comes to solving problems that would otherwise be complicated. So let's first talk about the uses of Gauss's law. So the uses of Gauss's law are pretty straightforward. You can either find the electric field given some charge. So if you know that you have some amount of charge or some distribution of charge, you can find the electric field in some cases that charge produces. Or you can find the charge given some electric field. So if I tell you what the electric field is in some region, then you can use it to find the charge that produced that electric field. So you might look back at the integral form and say, oh, that looks hard because surface integrals are hard. But it turns out that we really only use Gauss's law when we don't have to actually do the integral. And I'll explain how in a minute. Unrelatedly, Gauss has a lot of things named after him. So if you just Google Gauss formula, you're not going to get what you think. There's like a whole Wikipedia page titled "Things Named After Carl Friedrich Gauss." There's just a lot of things named after him. He was a big deal. Right, so the question is how do you use the integral form of Gauss's law without doing an integral, right? It's in the name. And the way that we do this is we apply symmetry arguments. He's like the Alexander the Great of all of mathematics and physics. Like, it's not just magnetism. It's like he shows up in my research all the time. Like, everything's named after him. He shows up in physics literally everywhere. Like, everything is named after him, either him or Riemann or Euler. Like, those three names, they're like everywhere. Anyway, right. So we apply symmetry arguments to make the integrals very easy to do. So the general method that we use when we apply when we want to use Gauss's law to solve a problem is we construct an imaginary surface. So the surface isn't given to you. Like, the surface that you do an integral over is not given to you. And this is often called a Gaussian surface. And we want that imaginary surface to pass through the region of interest, or the place where we want to know the electric field. So this is an important thing to realize. So when you're doing Gauss's law, sometimes the surface will be given to you, but generally you're just given where the charge is, and you have to come up with a surface that will let you compute the electric field at a place you're interested in. So once you do that, once you come up with that surface, then you can apply Gauss's law for that surface, that imaginary surface that you came up with, to establish a relationship between the electric field on that surface and the charge that is enclosed by that surface. And so if you pick your surface judiciously, then the flux, which is computed by just doing an integral over of the electric field over the area, is just a multiplication problem. It's not actually an integral that you have to do. And then the enclosed charge is just whatever it is, and usually it's pretty easy to compute. So when I say choose judiciously, what I really mean is that we use symmetry to pick our surface. So specifically, what I mean by this is that in order to make this integral easy, we need that the electric field must be, and these are characteristics of the surface that we're looking to choose. The electric field must be either parallel to or perpendicular to the surface everywhere on the surface. So in layman's terms, what that means is either, if you like for example, take the sphere and a point charge in the middle, either the electric field points straight out of the surface at every point on the surface, or it points along the surface. The caveat, or rather the consequence of that restriction on the surface that you choose gives you that the electric field dotted into the surface element is either the electric field times the magnitude, like the magnitude of the electric field times the area, or it's 0. So if the electric field points straight out of the surface, then it's just the product of their magnitudes, and you get this one. If the electric field is parallel to the surface, if it goes along the surface, then you get 0, because dA points out from the surface, and the electric field points along the surface, and so those are perpendicular to each other, and so you get that the dot product vanishes. So we should see certain surfaces a lot like cylinders or spheres. Yeah, cylinders, spheres, boxes, things like that. So the second thing that we would also like to have in order to use Gauss's law very straightforwardly, we would like that the electric field on the surface where the electric field is perpendicular to the surface must be constant. So not only should the electric field be either perpendicular or parallel, but in the places where the electric field is perpendicular to the surface, we have to have that the magnitude of the electric field doesn't change regardless of where you are on the surface. So what that gives us is it gives us that the integral of the magnitude of E times dA, which is what we got from this first step, that would be equal to, because the electric field is constant on our surface, what does that say after surface? Where? It says where. Sorry, that's a W. It's a very sloppy W. That still looks like a CO. There we go. Because the electric field is constant on the surface, that means that we can factor it out of the integral. And so this just becomes the integral, or sorry, the magnitude of the electric field times the integral of dA. And the integral over a surface of the surface element is just the area of that surface. So this is just E times A, where A is the entire area of the surface that you came up with. And so what these two things do is, if you have a surface that satisfies these criteria, you can split the integral up into parts that have parallel and parts that have perpendicular electric fields. You drop the terms that are parallel because those just vanish, they don't contribute at all. And then the parts that are perpendicular, if the electric field is constant on those places, on those parts of the surface, then the integral just becomes the product of the electric field in the area. That's why this is so strong, because you can use these sorts of things. So put together with these criteria, and again, I'm going to ignore the parallel part because it just makes things messier, but hopefully you can see how this generalizes. We get that the electric field, or the integral of the electric field, dot dA is just the product of E times the area of the thing that you're integrating over. So let's do an example. So we're going to do an example of something that we've already computed so you can see that the answer is correct. So we're going to do the infinite plane of charge. So we already know what the electric field should look like for an infinite plane of charge. It should look like sigma over 2 epsilon naught, where sigma is the charge density. This is a infinite, we put uniform plane. So sigma is the charge density, and and epsilon naught is just the number, and so the electric field should be sigma divided by 2 epsilon naught. So let's actually work this out. So let me draw a picture. So here's our infinite plane of charge. Imagine it extends in all the directions. You have a whole bunch of charge. We know what direction the electric field points in, right? It points outwards. Points straight outwards with a fixed magnitude. So hopefully, even if you didn't know that, you would be able to argue by symmetry that the electric field has to point straight outwards. Maybe you wouldn't know that the electric field is constant, regardless of how far away you are, But you should certainly know that the only direction it can point is straight outwards from the plane, or straight inwards if it has negative charge. Oh, and the electric field also points at the back too. So you would be able to make an argument from symmetry that the electric field only points in, say, the z direction. Let's say that that is the plus the z direction. Just because if it pointed in any other direction, it wouldn't be symmetric. And you know that there's the same amount of charge in any direction. So the only direction it could point is out. So what we need to do is we need to choose a Gaussian surface that is perpendicular or parallel to the field, or to this parallel to this straight outward field everywhere. So the Gaussian surface that we can choose then, not a plane, because remember it has to be closed. It has to there has to be an inside and an outside. A box would work, a cube would work. I'm going to use a cylinder. All of them will work basically as long as you have a flat side on this side and a flat side on this side. It can be, and it's something that runs long ways in the other direction, you're good. So I'm going to use a cylinder, but it doesn't matter. So that cylinder does not start with an S. So a cylinder with axis perpendicular to the plane. By the way, there is a good reason to use, so we're not surrounding it, we're enclosing a chunk of it. So let me draw a picture. Oh, and I'm also going to say that the cross-sectional area is A. Just so we're giving it a name. And maybe length L. So the picture here, I'm going to flip the plane so it's a little bit easier. So we have our cylinder here, which goes down, passes through the plane, comes out the other end. Oop. Right, and the area of the cap is A. It's just the cross-sectional area, and this distance here we're going to call L. Doesn't matter what we're calling it, it's just giving it a name. And then there's a whole bunch of charges here, and we know what direction the electric field goes. The electric field goes this way and that way, right? And we know that without knowing anything, without even knowing the answer to this problem already. We know that those are the directions the electric fields have to point, because that is because of the symmetry of the problem. Because we know that if it pointed any other way, then you'd be able to rotate the whole thing and it would look different. And an infinite plane should look the same regardless of what angle you look at it from. So with this surface, the electric field is parallel to the sides and is perpendicular to the caps, right? So that has to be true. So the electric field runs upwards, just like the sides do. And the electric field also runs upwards, whereas the cap, is horizontal. And so what we can do then is we can write that the integral over the entire cylinder, because this is an integral over the surface of the cylinder, by the way, because you have to do the integral over the whole thing. The integral over the cylinder dot dA, this is secretly equal to an integral over the sides, the side surface. This is not a closed integral now, of E dot dA. So think of it as the cylinder has three parts. It has the side, which is the thing that goes around, and then it has the top and the bottom, right? Plus an integral over the top, E dot dA. All we're doing is we're splitting an integral, which we can always do, plus an integral over the bottom, E dot dA, right? So all we've done is we split it up, but the important part, nope, not that. The important part is that the integral over the sides is 0. And the integral over the top and the bottom, well, the electric field doesn't change regardless of where you are on the cylinder, right? Because you're always the same height above the plane. So the electric field is constant and perpendicular, so we can factor it out. So here we would have the electric field times the area of the top, called A conveniently, plus, and then the same occurs on the bottom. Now, again, we actually have to make the argument that the electric field points in opposite directions going up and downward. But that should be, you can make that argument from symmetry as well, because it shouldn't matter whether you flip the plane or not. It should be the same both ways. So if it pointed in one direction, like if it pointed upwards from the bottom and upwards from the top, then flipping it would make it look different. So they have to be pointing either in the same, they have to be pointing in opposite directions. It might, we might just not know what direction they both pointed, either both inward or both outward. Right. But regardless, using that symmetry argument, we get that this is just the electric field times the area of the top plus the electric field times the area of the bottom. And that's just because the electric field.
Sorry, did you hire someone to come by?
Yeah, they come by every 3 months. Sorry, the exterminator's here to exterminate everything. The electric field is perpendicular to the top and bottom. And so that just, so the integral simplifies greatly. And so what we're left with is that from Gauss's law, that twice the electric field times the area, the cross-sectional area, should be equal to the enclosed charge divided by epsilon naught. No, we're exterminating Gauss's law. So the question is what is the enclosed charge? How much charge is enclosed? Well, consider that this region there, that is the only place that actually has charge inside the cylinder, right? So if we want to find the amount of charge inside the cylinder, all we have to do is we would have to do an integral, like a polar integral of that region, and we would integrate the charge density by the area. So basically, we just need to figure out a way to add up all of the charges inside the cylinder. But because this is a uniform plane, the charge on a given area of the plane is just the area times the charge density. So in this case, Q enclosed is just the area, or it's just the charge density, sigma, times the area times the cross-sectional area. Think like a cookie cutter stamping down on the plane. The amount of plane that you cut out would have an area A, and so the amount of charge would be the charge density times that area. So this is all to say that we can then just solve. So we get that twice the electric field times the area is equal to sigma times the area divided by epsilon naught. And then we can just do algebra to this, and we find that the magnitude of the electric field is sigma divided by 2 epsilon naught. And that actually agrees with what we found on last week. That is the same answer. So the thing that makes this easier is that all you have to do is think about it rather than actually going through a whole bunch of lengthy calculations. Like when we did this originally, we had to do an integral for a finite disk, and then we took a limit, and it just took quite a bit of effort. Once you understand the system well enough, you can make these types of symmetry arguments, and then we can solve. So the point is we assume that the electric field is constant along the surface or along the end caps, right? We're not assuming that it's constant at different heights, right? We didn't have to assume that at all because the end cap of the cylinder is all at the same height. And we know that it will be constant along the end caps because the symmetry of the system indicates that it doesn't matter where horizontally your electric field is, it should all be the same. It's just vertically it might change. The integral of the side is 0 because the dA points that way, it points outwards from the cylinder, and the electric field points upwards. And so the dot product of those two things is 0. So actually what we figure from this is that the reason why the electric field is constant is because the area, the only thing that changed or the only thing that affected the distance that the end cap is from the plane was the sides. If we had to do the integral of the sides, then L would have showed up because the area of the side is 2 pi times the radius times the height, right? But that whole integral was 0, so it just didn't depend on the area of the sides at all. And so that height, that L term, just drops out 100%. And then the area drops out as well, and we're left with just a constant. So it's a super easy way to solve a problem as long as you think about it appropriately. And so the point is this electric field applies everywhere because we didn't specify anything. We specified just the length of the cylinder and just the area of the cylinder, and that's it. And we could have made a really long cylinder or a really wide cylinder, whatever. So the thing is this question didn't ask about a cylinder. We came up with the cylinder to solve the problem. So that's the whole point of Gauss's law. You come up with the surface that lets you solve the problem, because the problem was just what's the electric field above an infinite uniform plane of charge. The cylinder was not baked into the problem at all. We chose that cylinder. That's an important point to take away. Let's do another example. Let's do the field outside an infinite conducting cylinder. Sorry, an infinite conducting plane. Well, the cylinder is perpendicular to the plane. But if you had, no, because then the electric field wouldn't always point outside. Like if you had tilted it, if you had done like a cylinder like this, then the electric field wouldn't always point directly outward from the cylinder, right? I mean, the flux through the cylinder would be the same for the same cross-sectional area, but the point is you wouldn't have been able to solve the problem with that choice. But by the way, you could have used a box just as well, a cube or anything. As long as it has straight sides and a straight top and bottom, it will still work. Right, so let's do the field outside an infinite conducting plane. All right, so here I'm going to have an infinite conducting plane. It's going to be, I'm going to assume it's relatively thick for now, but it extends in all directions. And there's infinite conducting charged plane, or so the plane. So this is not an infinitesimally thin, or I'll just say charged. Yeah, I'll say plane, but it doesn't have to be an infinitesimally thin plane. It's just some thickness, and we're zooming in a lot, so it looks really thick. So we have a whole bunch of charges that are distributed however which way on this plane. It's just a chunk of metal, right? Maybe a plate would be good. And so the question is what surface do we use here? Well, it has the same symmetry as the system before, right? It still has that same symmetry because it extends in all directions except the outward direction. So the symmetry indicates that the electric field points out. We don't know what the magnitude of the electric field is. But we know that it points out. And that's just, it just has to be true because it's infinite in extent. And it has the same symmetry as the plane. So we can still use a cylinder. So here, the cylinder, yeah, so it does point out. Here, the cylinder, well, we don't know anything about what happens on the other side of the plane, right? So we can't really say what the electric field is over there. This is only on one side of the plane. But what we can do is we can stick the cylinder halfway in. And then just let it be whatever it is on the inside. That's supposed to be straight, by the way. Yeah, so the charge is just on the surface, and that's a good point. We know that the charge always distributes itself on the surface of a conductor. That's something that we talked about before. So here, the electric field, remember from before, inside a conductor is always 0. So we actually know what the electric field is on the other side. So we know that the electric field is 0 in here. So we only have to worry about what happens on the outside. So we do a similar computation, and now we get that, so along the sides, the electric field is still parallel to the cylinder. But no, so the point is the Gaussian surface, these cylinders, these are not real. They're mathematical tools to help us calculate. They're like, because once you introduce a real thing, it doesn't have, like, the flux there will change. It helps us calculate the electric field is a real thing. And these Gaussian surfaces help us calculate that real thing by introducing some imaginary thing, something that exists only in our minds. Right, so it won't have an integral for the bottom. So here we have that an integral along the sides is 0. That's still true. But also, the integral along the bottom is 0. And that's just because the electric field is 0 there. It doesn't have anything to do with the geometry, whether it points outwards or whatever. It's just 0. So what we're left with, looking up at the result, the top result still works. It's still just the electric field times the area. But the bottom result isn't there. So what we're left with is that the electric field times the cross-sectional area A is equal to the enclosed charge over epsilon naught. Or, and this is with surface charge density, sigma. Now, here's where things, so if the surface charge density is constant, well, yeah, we're going to assume that it's constant initially. Then, if that's the case, then the enclosed charge is just sigma times the area. Then the electric field is just sigma over epsilon naught. And again, this agrees with the result that we showed, I think last lecture. I think, yeah, it was definitely last lecture where we talked about the electric field outside of a plane charge, outside of an infinite conducting charge plane, right? We showed that already. But we can get rid of these assumptions. We can get rid of the assumptions from before. I mentioned that, so I told you in last lecture that this is the electric field, the magnitude of the electric field near a conducting plane for any shape of plane. And I told you that Gauss's law would let us get rid of the assumption that it has to be infinite and it has to be a plane and things like that. So I'm going to explain how that works. So if we make the area very small, then regardless of the orientation, regardless of like how wavy and wobbly the surface is, then dA is always perpendicular to E. To E near the surface. Right, so the idea is, let's say you have some conductor that looks like this, and you're saying, well, wait a minute, the electric field is just, it's pointing every which way because it's a conductor and, you know, it just has to be whatever it is. But if you zoom in enough and make your area small enough, this just looks like some plane, conducting plane. And then we just use a really, really little cylinder. And this will tell us what the electric field is at that place. So the point is if you use a small enough area, you look in a small enough region, we get that the electric field anywhere on the surface of a conductor, of any conductor actually, is given by, and I'm just going to use the variable x here as a stand-in, but it's just some variable that describes the surface. The electric field is sigma of x divided by epsilon naught, and it points perpendicular to the surface. And that's because an electric field always has to point perpendicular to a conducting surface. Otherwise, the charges would rearrange themselves until it was. Yeah, it gets classically infinitesimally small. Yeah, all of this is classical. So the point is even if it's the word after E. What word after E? Near, sorry. So even if so x is just some variable. So maybe x tells you, describes moving along. It could have been x and y. It could have been x, y, and z. The point is x just tells us where we are on the surface. And so it's possible that the surface charge density varies with position. But as long as you make your area small enough, the surface charge density basically behaves as if it's a constant. Similarly, the curvature of the surface will behave as if it's flat. X is just some way of coordinatizing the surface. And so the point is we can apply this argument as long as we zoom in enough For any shaped conductor and for any distribution of charges on that conductor, this argument applies if you zoom in enough. And so this actually tells us the magnitude of the electric field on any conductor, as long as you're near the surface. Once you get further away from the surface, this is an approximation that breaks down. Yes, this is only for a conductor. This is an approximation that breaks down because, you know, if you could have like a conductor that's shaped like this, and then the question is, what's the electric field there, right? The electric field would get contributions from everywhere. So in that case, like, it will get more complicated. But near the surface, this will be the correct answer. All right, let's do another example. Let's do the field of an infinite line charge. So this is another example that we've done. I'm going to say infinite uniform. I'm going to put lambda there. That's our linear charge density. How near the surface is considered near? It's just near on the scale of the system. So like, if the system you know, changes its magnitude like every meter, then maybe you'd want to be in the millimeter range. If your object is like a sphere of radius 1 millimeter, you'd probably want to be in the micrometer range. It's just like this is like the same thing where we say that like if r is significantly less than d, then r squared over d squared is significantly less than 1. It's the same type of near. This is exactly true at the surface, and the approximation gets worse as you get further away. So for the field of an infinite uniform charged line, or line charge, lambda being the linear charge density, we can also use Gauss's law to find the electric field of that. So what's the symmetry? So the symmetry of the problem is that we know from, so we can just draw a picture, right? We know that the electric field can't point like at an angle, right? Because you should be able to flip it, and it should be the same. And you should be able to rotate it, and it should be the same. So the only way to make that true is if the electric field points radially outwards. I'm trying to draw this in 3D, but it's kind of hard to do. So it points outwards from the line charge in all of the radially outward directions. So the symmetry is that of cylindrical symmetry, right? You can rotate it, you can flip it. You can't just tilt it though. But if you rotate it any which way, or you flip it upside down, it'll be the same regardless. So cylindrical symmetry would suggest that we should use something that has the same symmetry as our Gaussian surface. But just as an aside, yes, that's exactly what we're going to do. So in this case, just to formalize this, the electric field points out from the line, and the electric, because it's uniformly charged, this is constant at any height. So the electric field has the same magnitude up here as it does down here. We actually did an example where a cylinder is not a great idea. For a point charge or a sphere, a cylinder would be a bad choice. You would want to use a cylinder or a sphere there, not a cylinder. No, so this distance, that is maybe the radial distance. This distance is height. I'm just saying, as you move up and down, the magnitude shouldn't change. It might change as you move in and out in the radial direction, but because it's infinitely long, it should be the same at like any height along the line, right? Could I explain what symmetry is, or what the symmetry of this system is? So the symmetry of this system is cylindrical because if you take an infinite line of charge, it shouldn't matter how you rotate it, right? It should look the same. Like any experiment that you do on the system shouldn't matter if you rotate it, because everything is distributed in like a uniform way. And so that means that there's some sort of rotational symmetry in this direction. If you rotate it that way, nothing will change. Similarly, you could flip it this way, just do a 180-degree flip, and it should also stay the same because the charges aren't changing. Nothing is changing about the system. And so that indicates that the electric field can only point outwards, because if the electric field, say, pointed upwards, then flipping it would make the electric field point downwards, and it has to look the same when you flip it. Similarly, if the electric field like pointed in a circle like that, then rotating it would change the electric field at any point. So it has to point outwards, and hence we can use the cylindrical symmetry of the system. So the Gaussian surface that we choose would be a cylinder that wraps the line. So let me draw a picture just so you can see. So it'd be like you put a cylinder here, like that. And we know that, say, for some cross-section area, the electric field will point that way, it will point that way. The electric field is pointing outwards. And coincidentally, all of those outward pointing electric fields are also pointing precisely outwards from the cylinder. Yes, this time the caps are 0. So from the symmetry, from these two statements, let me not do that. We have that we can find the flux relatively easily. An integral over the cylinder, this is a closed integral because the cylinder is a closed thing, of E dot dA. And let's give this let's use L for the height here and R for the radius. Just so we have names so we can actually do the computations. This would be an integral over the sides of E dot dA plus an integral over the caps of E dot dA. But in this case, the integral over the caps is 0 because the electric field points outwards and the vector dA points upwards. So in that situation, here we have that this integral is 0, and now we have to compute that integral. But we already said that the integral, or that the electric field, should be constant along like the can, like the side of the can, right? Imagine that this is like a soup can or something. So we can factor out the electric field, and then it's just an integral of an area. And when you do an integral of an area over a surface, you just get the surface area of that surface. So I'm just going to call that A sub RL. That is the area of like the wrapping of the can, like the sides. So whatever that surface area would be. Right. And so because we've done that computation, the electric field times the area of the sides is equal to the enclosed charge divided by epsilon naught. That's Gauss's law. The caps are 0 because the electric field points along the cap, and dA points up. And so the dot product of those two vectors is 0 because they're perpendicular. Basically, anytime the electric field runs in the direction of the surface, it doesn't contribute. That's A sub RL. It's supposed to be like a curly L. There we go. So now the question is, we're almost there. We have an E there. Now we just need to figure out what the enclosed charge is. So Q enclosed is the amount of charge. It's the amount of charge in the segment of line inside the cylinder. So it's like this, it's the amount of charge that this chunk of the line has, right? So we just need to find that, right? It's just lambda times the length. And so what we have, so this is just lambda times L, because it's a uniformly charged line, so we can just multiply the length by the linear charge density. And so plugging that in, we get that magnitude of E times the area is equal to lambda L over epsilon naught. And now we have to go and we have to compute the area, the surface area of the side of the can. That's just a problem in geometry. It's just the circumference times the height. So this is 2 pi r times L. And so the electric field then, the magnitude anyway, is lambda over 2 pi epsilon naught times r. And you'll remember that is the answer that we got before. So the electric field here isn't constant. And the reason it's not constant is because even if you make your cylinder bigger, you have the same amount of flux as your cylinder gets bigger, but the area that it's spread out over is larger. So you have the same amount of flux over a larger area. So that means less density of your less field line density, and so you have a weaker electric field. That's why the electric field goes down with distance, and this points radially outwards, of course. That was one of our symmetry assumptions. So if we wanted to know the electric field at some distance, say 5 meters away from the line, we would need to have used a cylinder that has a 5-meter radius, because if we want to know the electric field at that point, then we need to use Gauss's law at that place. Or you can just do it generally and then plug in at the end of the day. All right, another example. And I'm doing a butt ton of examples, which means that we're probably not going to get to where I wanted to get today, which is a shame. Maybe I'll assign some reading because I hate the method of images, but it's probably required. All right, one more example. Maybe we'll just continue with it on next lecture. All right, actually, there's 2 more examples. A whole buttload. Yep, so right, next example. Field inside a uniform sphere. By the way, I'm spending so much time on Gauss's law because this is probably like the most powerful tool that you'll have in 9C. I mean, Ampere's law is something very, very similar that you'll see near the end of the quarter, but this is like probably, if you learn one thing from this course, it's this. So far, everything that we've done has been about the field outside of a charge distribution. You have some charge distribution, and then we do some math and we figure out the electric field outside of it. But Gauss's law is just a fact about our universe. So you can use a Gaussian surface that's inside a charge distribution just as well. So let's do a sphere of charge. So we have our sphere, has radius big R, right? So we already know from the symmetry of the system, there's only one direction the electric field could point, and that's straight outwards from the surface, right? Like, it's spherically symmetric, so the only direction that it could point that stays the same regardless of how you rotate it would be straight outwards. And this implies that the electric field is constant at a fixed distance away from the center. And it implies that the electric field points radially outwards. So yeah, our Gaussian surface is going to be a sphere. That's the only sensible thing to do. So we could do 2 things. We could put a sphere outside the sphere, or put a smaller sphere inside the sphere. So we're going to do a smaller sphere. But first, we're just going to assume that we have some arbitrary size sphere. Maybe it's bigger, maybe it's smaller. Give this a size, our Gaussian surface has size little r. So every single point, like there's no place where the electric field is parallel to the surface, so we would just get that the flux, remember the flux is the integral. This is just equal to this over the sphere of radius r. This is just equal to the electric field dot dA, which simplifies to just E times the area of the sphere of radius r. That's all it is, right? So, and by the way, nothing I've done so far assumes that little r is bigger or smaller than big R. Like, I haven't made any assumptions yet. This is true regardless of the electric field. This is just flux. And so what we have is that the electric field, and I'm going to write it as a function of r, by the way, because it may very well depend on distance, times the area of the radius, times the surface area of the sphere of radius r. This should be equal to the amount of charge enclosed by that sphere of radius r, say, divided by epsilon naught. And just as a quick note, a sphere of radius r is 4 pi r squared. It's the surface area. And so what we get is that the electric field, the magnitude of the electric field as a function of distance from the center is the enclosed charge divided by 4 pi epsilon naught r squared. Now, there's two separate scenarios here. If little r is bigger than big R, then the enclosed charge is just equal to the total charge of the sphere, right? Because it doesn't matter if your sphere gets bigger and bigger and bigger. It's the same amount of charge. So it'll just be some fixed number, which would be the electric field. Sorry, the charge of the sphere divided by 4 pi epsilon naught r squared. That's just the answer. Now, if little r is smaller than big R, then the enclosed charge actually does depend on the size of the sphere, right? Because if your sphere gets smaller, you enclose less charge. And so then we have to actually find the enclosed charge. In this case, because it's uniform, homework 2 is not up yet. Because it's uniform, the enclosed charge is just the uniform charge density times the volume of the sphere of radius r, which is just equal to 4/3 pi r cubed times rho. So in that case, the electric field as a function of r is rho r divided by 3 epsilon naught. So what we're left with is two possibilities. We have the electric field is either rho r divided by 3 epsilon naught. And by the way, you could solve for rho in terms of capital Q and the radius big R. I'm just not going to worry about that. Or, and this is when r is less than big R, or it's just equal to Q of the sphere divided by 4 pi epsilon naught r squared when r is bigger than big R. And so that just is the electric field at every point in space around a sphere. So if we wanted to know it here, we know that our little r would be bigger than big R, so we would read off our answer here. If we wanted to know the electric field at some point inside our sphere, this is not a conducting sphere, by the way, then the electric field we would read it off from here. And so note that if you were to plot this, the electric field, the magnitude of the electric field anyway, looks something like this. It goes up and then it goes down. And so an important, it doesn't actually hit 0, it asymptotes to 0. But an important point is that there is continuity, which is that E of R slightly E of R, how do I want to write this? This is what I'll do. No, that's terrible. I'll just say it in words. Yeah. So if you plugged in little r is equal to big R into both equations, both solutions, you'll find that they're equal to each other. But the reason they don't look equal to each other is just because we've used rho in one of them and capital Q in the other. But you can relate rho and capital Q by the relationship that capital Q is rho times the total volume. And so once you get that relationship, you find that they actually match at the edge of the sphere. And that's a good check, because the electric field shouldn't jump from one value to the other. It should be continuous at every point in space. It might not have a continuous derivative like it doesn't here, but the actual value of the electric field should be continuous. And that's a good check for physicality. So just as a little bit of more examples for you guys, I have a whole bunch. I'm not going to do them, but I'm going to tell you about them. So there's a related example. A related example that solves this problem using the local form, which is in section 1.7, and it's just above 1.7.1 in the LibreText. And this does this in the local form. It solves the same problem using the local form of the Gauss's law. Then there's another example that is useful. Again, section 1.7, and it's example 1.7.1. Here, this is using Gauss's law to solve a problem that has a long, hollow, insulating cylinder. Not hollowing. It's just another Gauss's law example, finding the electric field for that. Then there's a few more examples that are in the lecture notes. They're from the University of Physics online textbook. One of them is for a non-uniformly charged sphere, uses Gauss's law to solve that problem. Another one is for a uniform cylindrical shell, and the links are in the lecture notes. One final thing I want to talk about, God, I did not get nearly as far as I would have liked to, because I still have all of method of images to talk about. Maybe I'll just assign some reading for that, because we do need to talk about it. Right, so the last thing to talk about is we can use Gauss's law to understand what happens inside of hollow spheres. Well, if you guys, actually, I will instead just tell you to go look this up in the textbook. It's at the bottom of section 1.7. Please go look at this. This is official material in the course, responsible for knowing it. So it's like 2 paragraphs at the end of the section. But go look at it, ask some questions in the Discord if you have them, but 100% totally necessary to know. The bottom line is that we can use Gauss's law to figure out what the, or how the charge is distributed on the inside of a hollow conductor. Like if you have a point, charge inside a hollow conducting shell, you can use that to figure out how the charge is distributed on the inside edge of the shell. It's really neat, but don't have time for it. Yeah, lecture notes will have, well, I might cut off some of what I'm going to do. We still have a few minutes. I just want to talk about this remaining thing, which is the method of images. And I hate the method of images, and I wish it wasn't in the curriculum, but it is, and it's not my choice because the person writing the final told me that this is fair game. So, so it has to be done. So the method of images, and maybe I'll just give you like a little sample of this, and then we can talk about it more on Monday, is the method of images is a way that we can calculate hard problems. So for example, what happens if we place a charge near an infinite conducting plane? An infinite conducting plane. I can't tell you who's writing it. So just as a reminder, the electric field has to enter a plane perpendicular to it because it's a conducting plane. So if we put a charge here, that electric field will just go straight in, but these will curve to enter parallel or to enter perpendicularly. And these ones, will loop around. And this picture that I just drew should look super familiar because it's basically just half of a dipole. And you wouldn't be wrong for thinking that that's all I drew, because that is all I drew. And it's not just a similarity. Mathematically, the field from a charge near an infinite conducting plane is identical to the field on the right half of a dipole. Like mathematically identical. So this would be like putting a plane right there and then only looking at the right half, right? The fields in both cases on the right half are precisely the same. So the fact that these two fields, like even though they're completely different systems, the fact that the fields are the same allows us to solve hard problems. That's not how you spell equivalence. The equivalence of fields lets us solve hard problems. Using simple tools. So we already know how to find the electric field from 2-point charges, for example, but we don't know how to find the electric field here. So we could just use this picture here, find the electric field wherever we want, and then say, oh, well, that's the same electric field as it would be if we replace the other charge with a plane. Does that mean that if any charge is put in front of the plane, does it bend the entire field of the whole plane? I don't precisely know what you mean. So
like before we had. Oh, sorry.
I'm just going to end the recording here. Leave you on a cliffhanger. We'll talk about it more on Monday. But this is it is a useful tool, even if I hate it.